months ago that's simulating nanoparticles and cell membrane interactions. This is part of a bigger effort of a European project called Membrane Nanopart, where we try to address this problem of how nanoparticles and cells membrane interact, and in a way we try to propose computational tools to predict the toxicity of these nanoparticles. So the idea, if somebody tells me I just designed this nanoparticle with this characteristics, try to predict if it's toxic or not. So let's see, that's the main big aim of the project. So now you can ask yourself why it's important to study this nanoparticle membrane interactions. Well, and nowadays there's a quite big interest in studying and designing nanoparticles, for example, to do drug delivery. So I think there was a really famous paper about a year ago where people proposed, well, if I get a nanoparticle, engineered the tiny nanoparticle coated with some special proteins, then I can deliver some kind of medicine to cells that are cancerous, for example, and that will be chemotherapy, really specific. So it will attack only the cancer cells and not the good, let's say the healthy ones. So, but then you ask the other question. Okay, you can do it for that proposal, but what happens? Are those nanoparticles toxic? The people who made them and build them, they're exposed to those for long times, and are they going to have any kind of reaction to those, like happened with asbestos, I don't know, 20 years ago. So that's why it's important to study the toxicity of these things. So now let's see. This is a scheme, an oversimplified scheme of what can happen when a nanoparticle meets a cell membrane. So first you have the nanoparticle, then the nanoparticle it's immersed in a medium. So if it's in your blood, it's emerging, let's say it's moving around your blood, or if it's in your lungs and the fluids in your lungs, then there's a solid liquid interface between the nanoparticle and the membrane. Then in the membrane, you also let's say the typical model that we use is a lipid membrane. I'll explain a little bit what's that in a second. But also that lipid membrane can have like receptors, like special proteins that can attach to special proteins and stuff like that. And then the nanoparticle also, and it's, let's see, the picture that the nanoparticle goes interacts naked with the cell. It's too naive. It has been shown that usually when this type of nanoparticles are put in let's say in biological medium, they form a special they call it a nanoparticle corona. So the nanoparticle is coated with a lot of proteins that are found in the blood or in the fluid and whatever medium it was. So we have to address a lot of issues and let's say to predict the toxicity of these nanoparticles. And it's a quite let's say complicated problem, and you'll see we will try to simplify as much as possible. But again, trying to at least predict some toxicity properties of those particles. So what we are going to do, we're going to use a computational method, basically molecular dynamics, to study this nanoparticle membrane interactions. So the main configuration will be, we will have a lipid bilayer. This lipid bilayer can have all the types of glycoproteins inside them. Then we have a medium where the nanoparticles and the bilayer live. Usually that can be water, let's see, it can be the blood and your veins or something like that. And then you have the nanoparticle, which let's say we will try to address the issue that it's covered with something. So there's a nanoparticle corona form. So the main components of our model will be basically how to model the bilayer, how to model the nanoparticle, this nanoparticle corona interaction, and also aggregation between nanoparticles. So how can we do that? At the beginning, you can just think, let's see, if you don't think enough, we just do MD simulations. You can do M simulations of lipid bilayer, that's done a lot, and water. But the problem is that the time scales and the sizes of this, let's say, nanoparticles are too big to just simulate it with standard or full atomistic molecular dynamics. So you have to do something else. So, and let's see, the first solution you can think about is to cross-grain. And cross-grain here means that you have a full atomistic, this will be a schematic representation of a full atomistic MD simulations. So there you have, I don't know, one lipid and the water surrounding. So you gather together some of the atoms of those lipids or protein or whatever you're trying to simulate, and you now form this bead. And this bead will be just a collection of those nanoparticles. And then, in the case I'm going to speak here a little bit later, we try to get rid of the solvent also. So it will be the water in that case. And we will manage to do that in something that's called DPD scheme.
So the beads in your relative to your previous picture are representing the lipid bilayer.
And the nanoparticle also.
The nanoparticle cell. Yes.
Yeah, exactly. Yeah, in a while I'll show you exactly one example. Yeah. But yes, that's it. And that's the main problem here. How to model it, how to do it. So just to get a bit of a context of what has been done in the literature before, there are plenty of works on computer simulation on nanoparticles and membrane, but most of them are for really, let's see, usually there are classical MD with Solvent, and well, sometimes with DPD and coarse grain and the whole thing, but usually nanoparticles are less than 10 nanometers, which is, let's say, for application, that's not quite good. And usually they're bigger than that, 50 or so, 100 nanometers. And the bilayers, of course, are really small, the ones they can simulate, because a lot of the time it's just spend calculating stuff related to the water outside. And so they're around 30 to nanometers square, 30 by 30 nanometers square. But apart from that, they have seen, for example, you can see acidity of the nanoparticle. That means that the nanoparticle is wrapped by the cell membrane, and then it's internalized in the cell. You can see addition, you can see penetration and rupture. But we want to see this at other scales, let's see, bigger scales, and again, to try to predict the toxicity of those nanoparticles. Here were the nice pictures of what can happen. For example, the top one is one where the nanoparticle is wrapped and then it's internalized in the cell. One when it's just simple adhesion, also, and another one where it penetrates, and this one where it breaks the membrane. So what is this DPD method that I just mentioned? So imagine molecular dynamics. Molecular dynamics is just you have a collection of atoms usually, and those atoms are somehow you have to write forces for them. So how they move in time, and those so you can have bonding forces and you can have interaction forces between pairs of atoms, and at the end you just put that solve Newton's equation for a bunch of those together and try to study the dynamic. In the case of the PD, it's again the same, but instead of atoms, you have those beads that I just told before. And usually you have, let's say, normal MD will have this part, the conservative part of the dynamics. So there you will have your pair interactions of your particles. You will have the bonding interaction, the angle-dependent bonding interaction, and things like that. But apart, you have to add other two forces. We call one the dissipative force and a random force. And a bit, I'll tell you how they look like. And let's say if you ever see a work where they say we use MD with a DPD thermostat, when they refer to PD thermostat, they say they're using this bit of the equation only. So if you stick to if you use the dissipative term and the random one, that in a way keeps the temperature constant in your simulation, and they call it a DPD thermostat. And it's quite
First D in DPD dissipative.
Yeah. Sorry, I didn't never say it, but yes, it's dissipative particle dynamics. Yeah, sorry. And well, and those who like particles method, this is a method that, let's say, in some sense, it's closely related to SPH, to smooth and particle hydrodynamic. People say that smooth particle dynamics is basically a way to solve Navier-Stokes equation using particles, and they say if you go up from SPH and go down to mesoscopic scale, you obtain the DPD equations. The people from the DPD community, they say, no, you have to go the other way around, and then you recover Navier-Stokes. I guess it depends where you were trained. So again, the conservative part, usually in, let's say, in classical DPD scheme, It's a constant at AG, so there will be a constant for every pair of interactions of particles that you have, and it will depend on this weighting function, that it goes to 0 after a cutoff radius. So you have a cutoff radius, and those A, I, J will be the maximum repulsion between particles, basically. So when they meet at R0, they repel with that force. But again, that's in the classical DPD scheme. But you can also use Lennard-Jones potentials. It's also valid. So let's say, or any other type of potential that you don't have to stick to that one. The advantage of using this type of formulation is it's called what people call soft potentials, is that then you can do much bigger steps in your integration. So then you can go to bigger time scales. But apart from that, you can also do Lennard-Jones potential without any problem. And then this is how they look, the two other terms.
I'm sorry, before you go to that, I didn't understand. So the AIJ is a constant?
It's a constant for each par interaction. So let's see, if I have a water, if in my system I only have water, it will be 1. But if I have water and another, I don't know, another substance, there will be 1 between water and water, 1 in between the other two, and 1 between water and the other. So you have to have 1 for each pair. Yeah. And okay, and here we have a term, the dissipative one and the random one. Again, they depend on the weighting function. Here, this gamma will be a friction coefficient, and that's where, well, let's see, the black magic comes, because there's no really physical quantities you can relate it to that. So you basically have to test it and see which one gives you the right dynamics and the right time scales. In a way, you can say the inverse of that number should give you the time your system reacts to the thermodynamic equilibrium. But apart from that, you cannot say anymore. But well, it's there. And the good thing is that there's another parameter, the sigma, and the random force. Well, this zeta ij is a random number, uniform. It has to be symmetric. It means that the ij is the same as the ji. And it has to have mean 0. That's, yeah, I guess that's it. But well, the gamma and the sigma are related by the fluctuation dissipation theorem. And that was, let's see, at some point when the method was first proposed, they didn't realize that, so you had 2 parameters. But now everybody agrees that you have to use the dissipation, you have to be related by the dissipation fluctuation theorem to have the right thermodynamics. Another thing about this methodology, if you use the DPD thermostat, is that it conserves momentum, linear and angular momentum. So there, in MD, there are other types of thermostats, for example, Allen-Jabine thermostat, but that doesn't conserve, for example, angular momentum. This one does. And again, in the conservative part, you can also add other types of interaction, like bonding interaction or 3 bending potentials and whatever. And it doesn't. You don't have to stick to that functional form. You can also use normal Lennard-Jones potentials.
Sorry, just another question.
Mm-hmm.
So the dissipative part, why do you have the square of this weighting function in there?
Pardon, the what?
The square, it's w squared in there.
That's another thing. If you go to the derivation of this, it has to be that way. It's the only way to get the right thermodynamical equilibrium. It has to be that way, and in fact, that was at the beginning. People were realized they didn't know the factor sigma, and they didn't know how to put the weighting functions there. And it's there. There's I cite a paper of Pep Español from Madrid, and it's there. The derivation is there. So now, again, we have the system, we know how to move our particles, but again, we have to define the potentials. So it doesn't matter if I cross-grain my system or do whatever I want, I still need to know what are those A's in the case of DPD, or what are my Lennard-Jones potentials, or the parameters of the Lennard-Jones potential. So how do we get that? Here I'm going to show you one option of how you can do it, and it's the one we are using at the moment. That is called inverse Monte Carlo. So the idea is you start from a full atomistic simulations. So you spend a lot of time doing that, and those ones you calibrated with experiment measures or whatever, and you believe those. So those are going to be your reference, and those are going to be your experiments.
Fully quantum mechanical?
you can do it fully quantum mechanical, but again, it depends on what you're simulating. So you can go and do ab initio calculations and fully quantum mechanical of your structure, but those you can only do maybe tens of atoms or something like that. So it's not you cannot even do a lipid molecule. So you're stuck to again do MD. But then there are ways to get the potential for MD from those simulations of smaller systems. But well, okay. So you have those, and from those you get structure. So you have the structure of your lipid or your protein or whatever, and from them you're gonna get your radial distribution functions. So after you did all that work, what you're gonna have is just a plot of the radial distribution functions of each type of particle with each type of the others, and that's it. And that's what you're going to use as an input to get your potentials, your coarse grain potential. And again, you have to coarse grain, so you have the whole molecule or whatever, so then each of those bits, you already did the coarse grain procedure, and then you're going to say, well, I replace all this for one only particle, all this bunch for one, and then that's the one you're going to find the potential for. If you want details, so you can find it on these references. So the basic idea is that you can, the Hamiltonian of your system, you can write it in this form, where K alpha are just constant, and S alpha are base of functions of that Hamiltonian space. So, for example, for a pair potential, so a pair potential between two particles, you can write the Hamiltonian as a sum over all the particles that you have, all the positions between all the particles. That's Q. Q is the position. Will be the distance, basically. This side will be your potential. And then you can just rewrite it at this form. And in this case, your alpha will be or your distance, then your K alphas, which are the ones who are gonna set up, let's see, what you're gonna give you the values of the potential. It's just the value of potential of each of those alpha. And then you, in this case, for a pair potential, your S are gonna look like this. It's just the number of particles on each distance, basically. So, for example, if now you say, well, let's say it's an arbitrary tabulated pair potential. So I discretize the distance between all the particles and say, in each of these points on my grid, I have an S, and then I average that. I do a simple average of that. I get that expression that's there as 1, where G is the distribution, the radial distribution function. So now I can relate a measure that I can, let's see, I can calculate by the result of my simulations with this average. Now I take just derivatives. So the important stuff here is that this relation here too, if I have a simulation where I have the radial distribution functions, I can calculate this term here, this derivative here, and I can also calculate the average of those S functions. So let's see, now let's see how it works, the algorithms. So suppose we do a really detailed simulations. We say now our S star is going to be our reference function. So now what let's see, the problem here is usually it's easy. If you have the structure already, you can calculate the radial potentials. But we want to go the other way around. So we don't have that. We have the radial distribution functions, but we want to calculate these contents who make let's say, unique one of those pair potentials. So then using the equations that I showed before, where basically you do it in a simulation, is you calculate each of these terms, see what is the difference of that. With that you can get a delta K here. Then iterative, put it again on the other, let's say correct it, put it again in the other equation, and do that iterative number of steps times, and you can get back your potentials. We give you the radial distribution that you started with, already coarse-grained. And here's a reference where they use this method to simulate a lipid bilayer. And in fact, there in that paper, I think, yeah, it's about a code where you can download free and do this stuff. If you already, I think it's made to use the output of GROMACS. GROMACS is one of those programs that people use in MD. So there are tools there that you can use to calculate this stuff. So at the end, this will give me a list of tabulated potentials for each pair of molecules that I want to study. Well, molecules of DPD beads. So now let's go to the model that we are working now at the moment. So usually in those nanoparticle membrane interactions, people use to represent the nanoparticle just a rigid sphere. But well, we are using another model that is described in that reference there, where we have a central bead and we have surface beads that interact with the central wire by Lennard-Jones potential, and then between each one of them they are just bonded by it. It doesn't matter why I have Fleming bonding potential, doesn't matter what it is, but they're bonded together. So in that way you can keep the structure quite solid of the nanoparticle, but you can also, let's say, not make it that rigid and add more details to your nanoparticle surface. And for the lipid bilayer, this is the model that we're using. So this is here, the DMPC molecule. It's this one. It's made up of 118 atoms. Doesn't matter. That's the lipids, and lipids in a way act like surfactants. So you have a head that is hydrophilic, and the tails that are hydrophobic. So if you put it in water, a bunch of those, they tend to the tails to gather together and let's say go out of the water, and the heads just to face the water, so they can form vesicles and bilayers. That's the one that we are interested in to model. And then here you can see now our cross-grain lipid model. So we went from 180 to 10. So that really speeds up a little bit more of the computation. But again, you lose information in the way, but we assume it's not that bad. And for the simulation, we are using a code named Espresso. It's open source and free available. So if you ever want to do something like this, I recommend that one. But there are others, no? So okay, now we have our pair potentials. We have we have our tabulated potentials, which we can put in our simulations. And in this case, I have a box of 15 by 15 by 15 nanometers. Initially, I just put 762 nanometers organized, lipids organized in a layer. I didn't tell before, I forgot. But the point where you take out the solvent, in this case the water, is when you recover when you did the cross-graining of the potential. So here, nobody says that you have to simulate exactly the same system that you had before. You can cross-grain and say, well, I'll take out the solvent, and still I can recover the same radial distribution function. So in this step is where you take out the solvent. So in this case, I just at the beginning, I just put them let's say 2 layers, and let's see. I think I did uniform organized on the top, and I just left the system to relax and do dynamics, and I get this really nice bilayer there that is stable for forever. You can leave it there simulating a really long time, and it's still going to live there. It doesn't really bend that much though, so the tension, I haven't calculated, but I assume it's almost 0. Here you, for example, see a density profile of one of those bilayers. You can see this will be the heads, and this is the typical way you see in a bilayer. The heads are facing outside, and the tails, which are here inside. And then we can measure the thickness of the bilayer, and in this case it's around 3.5 nanometer. And I think that the experimental value is, well, again, like an experiment, something in between 3 and 5, I think it is. So at least we are in the same region. No? We can also characterize, because I haven't said anything, but one of the problems with this TPD problem scheme is that you lose the time scale that you had with your molecular dynamic. Let's see. You have to somehow calculate now your new time scales. And one way to do it is you can measure the lateral diffusion of the lipids inside the bilayer, and then relate that to experimental values. So here you can see the lateral diffusion as a time. It goes to a constant, and then from that you can extract this T0 that will be our time scale. And this also proved that the biolayer is quite stable. So otherwise, the diffusion will do crazy jumps or always do something weird, but it's more or less stable there. So now we are ready. We have a nanoparticle model and we have a lipid bilayer that's stable. So let's put it together. Let's see what happens. And here's where let's see where the results are much more preliminary than anything else. They're a nice picture, basically. That is that because we haven't parameterized the nanoparticles lipid interactions, and that's the one that the people in Stockholm here now are working. And also, what I'm going to show here is just naked nanoparticle. As I said at the beginning, usually you have to add stuff around the nanoparticle to make it more realistic. So here are the results. At the beginning, you place the nanoparticle. I think in that case it was the nanoparticle's radius is 2 nanometers, so probably it was 4 nanometers upper end of the layer. I just invented some potentials there, and then just see what happens in time. And as you can see, as time passes, the nanoparticle gets fixed to the bilayer, and at the end there's an adhesion process there. And if you keep the simulation for a long time, much more long times than this, you can see that an nanoparticle just lives there and forever, and it doesn't do anything else. But again, this is really unrealistic. We have to still parameterize the other potential. So now, just to finish, let's make some conclusion here. So I just review one of the possible computational tools you can use to simulate membrane and nanoparticles interactions. The advantage of using this methodology is that you get rid of the solvent, so then you can simulate larger and bigger timescales. We simulated a nanoparticle, let's say, a layer by system, a toy model in this case, where we can see the adhesion of the nanoparticle. At the moment, I'm not showing here, but I'm, for example, changing the charge of the surface of the nanoparticle. This was a neutral one. We can play around and put a positive, negative, or whatever, and see what happens. And well, future work is to obtain force field for the nanolipid interactions, for the formation of the corona, and also study nanoparticle aggregations. So I think this was it. Yeah. So thank you very much.
So I know there are a lot of different attempts to model lipid bilayers with solvent-free models, and so I understand one needs to make huge approximations in doing that. But I was a little bit puzzled here. In your case, you're trying to coarse grain the lipid interactions in a realistic way using Lubartsev's method. But then you take the solvent away, and so of course a real lipid bilayer is stable for a variety of reasons. But one of them is that the hydrophobic tails want to stay away from the water. It's hard for me to believe your lipid bilayer will be stable. So I mean, if you put oil, for example, and then take away the oil, it'll be the same simulation.
Yeah, that's a good question, and that's something I didn't really believe at the beginning when I read the first papers to say, let's get this thing running. But it does work. For example, if you start from a random, you're going to put it in a box, and you start with a random arrangement of lipids all around the box. They gather together and they form vesicles. So those potentials that you are getting from the cross grain, they're really somehow representing that the tails like the tails and the heads don't like the tails at all. So it's
I just think, in the end, you're going to try to model a process in which the nanoparticle is going, it's going from water into a bilayer and then maybe penetrating. So there are a lot of free energies there that you really can't calculate.
Yeah, I think at the end what we're going to do is, let's see, it's not going to be a totally solvent-free. At some point we will have to cross-grain the solvent, but let's see, attack it in a more aggressive way than it's done before, so we can go to bigger scales. Yes, and you're right on that. And you're going to have the wrong dynamics if you don't include the water. Well, you can still study some kind of statistics, like statics properties, like free energies, but no more than that. The dynamics, yes, probably nobody's going to believe me if we don't include some kind of model for the water.
In one of your early pictures, you showed a relatively large nanoparticle and compared with the thickness of the lipid bilayer, and the lipid bilayer was sort of engulfing it.
Yeah, that's
Is that a matter of charge, or have you had that in one of your runs?
No, I haven't, and that's another thing. That's the thing that people. Well, you have to really you see the pictures and they look really nice, and you say, well, everything is done. But then in those simulations where they do that wrapping of the nanoparticles, because the bilayers are really rigid, let's say they want to be flat, they add in a special requirements on the boundary conditions. So they make it, let's see, really artificially, they make the nanoparticles, the bilayers flexible.
Because I mean, what it
That's the problem with it, and that's why we're trying to do it. It's not cheat from the beginning. So because you can really adjust all those parameters as you wish, and you can see whatever you want. So
what it made me think of was a rather larger length scale of bacteria causing themselves to be engulfed by the membranes of rather large cells, and in the gut or somewhere, and cause disease. So where a sort of but molecular dynamics as such would be useless because there's far too many molecules, but it seems to me possible that your distributed particle dynamics method might be usable on that large scale. Of course, on the large scale, you might get away with a continuum model, but maybe from your point of view, you'd like to derive the continuum model from your finer structure.
Yeah, you're right. Yes, that's sort of things you can do. And the problem is, again, you can find whatever you want in this kind of things because you can play around with the parameters of your potentials and basically.
Well, finding whatever you want isn't necessarily good enough. I mean,
that's the thing. That's what I'm saying. I know. That's exactly what I'm saying. That the point is that
modeling
it's so open that at the end you can do whatever you want. It's sometimes it's.
Yeah.
May I ask, when you modeled the last part, I mean, you said you assumed some potential between the nanoparticle and the membrane.
Yeah.
So I guess you made it like the inner part of the membrane. And if you want to engulf it, you need to make it like the outer part, but not the inner part.
Exactly. And you have to
membrane tries to go around.
Yeah. Oh, you can, for example, add a really big charge because I didn't say there, but the heads are positively charged, I think, and positive charge. The other way around, I don't remember. But you can do it a really charged nanoparticle the other way around, so you can get it that way also. But again, for example, this layer is too small to be flexible, so you have to really do it much bigger.
More questions. Let's start with Christian.
Why did you use this raspberry model for the nanoparticle and didn't just take a sphere?
Well, usually people don't use spheres. Usually they use a rigid body made of DPD beds. But we use that one because at the beginning, well, we think at the moment that at some point when we're going to study aggregation of nanoparticles and that, this model, the raspberry model, will be more useful.
Still don't understand quite the reasoning, because you can still make one big sphere and put some pair interactions on that.
But then
do you want to have more interaction centers for some reason?
Yeah, for example, the nanoparticle has a
question I had is, why did you use DPD in the first place? Because do you think that let's say hydrodynamic interactions will play a role here?
Well, yes.
Because you could just use Langevin type.
Yes, you're right. But again, yes, we think when aggregation between nanoparticles is going to happen, let's say you have at the end the idea is having your bilayer, you have some layer of water or whatever you have, and nanoparticles, their interaction between them, and then hydrodynamics will be important. Because they can aggregate between them and they can
Just to clarify, what you mean is like Brownian dynamics of many particles or something like this?
Brownian is the overdamped and Langevin is just when you work with inertia.
Yeah.
It would be for static properties okay. For dynamics, you anyhow have an artificial dynamics, and DPD has an artificial dynamics which can mediate hydrodynamic interactions due to this momentum conserving thermostat. I mean that's the advantage of having the DPD there. Normally you can have, let's say, smoother potentials with DPD which lead to larger time steps, and you can speed up the simulation, but all that I don't see that it's actually happening here.
No, this particular example that I did at the end, no, we're not using it. Again, it's when we, let's say, the DPD scheme will be really useful when we get into the point that we have several nanoparticles interacting in a medium.
If you don't have any solvent to mediate hydrodynamic interactions there, then
well, that's the point that I went before that we said at some point, yes, here we went over simplistic, and at some point we have to add some water there. Yes, we will have.
And you have to reparameterize your lipid interactions. And the next question I have then is, do you think you can make Liubartsev method? I mean, if you want to parameterize your nanoparticles with the lipids, and I mean this is a structural sort of coarse graining, but I got the idea that you probably would like to look at a dynamical process. So how realistic is it that this sort of structural coarse graining will lead to the right dynamics?
I'll take a question. We don't know. We have to do it and find out.
Against what do you gauge it then to find out if this is correct?
Pardon?
At what kind of system can you then gauge it and say, I see the right thing? I mean, what is the right thing? I mean, what is the right thing?
Yeah, no, there are lots of experiments for those. There are a bunch of experiments. In fact, there is a group there in UCD where they do experiments basically, and they have really nice experiments, and you have images of them, and they measure lots of things. So, yeah.
Like what?
They measure.
What do you think you can compare?
You can compare, for example, size of nanoparticles or shapes of nanoparticles and their rate of penetration in a membrane, for example. They have those sort of measures. Because they can also, for example, changing the environment where the nanoparticle lives, how that changes the penetration or not penetration of the nanoparticle to the cells and things like that.
There's one more little wrinkle to add to Christian's comments, and that is, of course, when you put the solvent back, one of the criticisms of DPD is that it produces a fluid in which the Schmidt number is approximately 1. So this means that from the hydrodynamic point of view, it's more like a gas, dense liquid.
Yes, there's no fluid. There's no flux when you do DPD. Yes. To do that, probably you have to do lattice Boltzmann or something different. So yes, and at some point we were thinking about doing lattice Boltzmann, but let's see, this is just good enough to begin with this, I guess.
And why not simulate the solvent as a canteen?
Well,
it means to introduce some potential in that.
Yeah, well, in a way, that if you do lattice Boltzmann, that's it. It's more or less that. It's not exactly that, but yes.
Could you do it in DPD, like you are doing?
I don't know if they have done it, but remember, the potential will depend on the position of all the particles outside, no? Because the solvents are also moving around, so I think it's not trivial.
Solvent is moving around, but it is the same.
Yes, I guess so. No, I don't know. I have to look at it.
There would have to be a thin layer, wouldn't there, between his beads and the continuum where you have to apply some sort of boundary condition. I'm not quite sure exactly how that would be.
Yeah, I have no idea. I think there has been
people doing this for totally different problem, nano indentation of solids. They couple local MD simulations with continuum models. I don't know how they do that, but I mean, this case is more complicated because you have stuff moving around. But maybe one should look into this.
I have seen at some place, but not in this context. In another context where they do things like that.
Thank you.
Okay.